All right, to start the class, I've got one simple question. Who here likes Oreos?
Everyone.
Oreos.
Everyone.
You'd be surprised. Do you guys like Oreos?
Yes.
Okay. The reason I asked that question is because I want to use a real simple example. What we're going to be talking about today is we're going to talk about how to maintain homeostatic balance. And the reason we're going to talk about this is because basically all of physiology is about maintaining homeostatic balance. All right? Now, what you're looking up here at, the slide describes, after we're going to go through all the details, is something that's called the law of mass balance. Now, you've been taught this before over and over again. You've probably never learned the name. There's another name that they use in chemistry called the law of mass action. Same principles, different words. All right? Now, I want you to imagine a plate with 4 Oreos stacked on top of it. All right? You are allowed to eat as many Oreos as you want. But every time you take an Oreo off the plate, you have to go to the cupboard, which has an infinite amount of Oreos inside. So the rule is 4 Oreos have to stay on the plate. You want to eat 1 Oreo? Fine. Take an Oreo, shove it in your mouth, enjoy. Take an Oreo, put it on the plate. How many Oreos do you have on the plate? 4. Always have 4. This is the basis of homeostasis. What we're trying to do is we're trying to maintain a constant internal environment in our bodies. Not Oreos. But the principle is the same. Constant balance. All right? We're trying to maintain constant temperature, constant water, constant solute concentration, constant protein concentration, constant hormone concentration, constant whatever you want to think about is trying to be maintained inside the body. So, what we have to do is we have to balance what we put in and what we make versus what we take out and what we destroy. Now I'll give you an example of something that we make and destroy very, very briefly. You guys remember from biology, or if you're taking biochemistry, I'm so sorry, glucose metabolism, right? Glucose plus, do you remember? Plus what?
CO2.
Plus CO2? No. Plus water? Okay. I'm trying to even remember the damn formula now in my head. I had the example all ready to go. Basically, you put glucose in your body, and what you're going to get out is carbon dioxide. It's glucose and oxygen, guys. Glucose and oxygen, that's what you put in, and what you get out. You make something. You make carbon dioxide, and you make water. All right? So, in essence, you're actually making water that your body is going to be using. And one of the things we do is we get rid of excess water by exhaling, right? So that's a way to get rid of something. All right? So we don't always have to input water because we're actually making water as we go along. Just our normal, natural metabolic cycles. All right? So really, this is what the law of mass balance is. And you see that picture up there, it's just describing the same thing, except I think Oreo cookies are easier than looking at, say, a bucket of water. Right? In order to maintain a constant volume, we have to add in the same amount of water as is coming out. All right? So for any substance in the body to remain constant, the gain must be equal to what you remove, equal loss. Gain includes things that you intake as well as the things that you actually make. An example I use, glucose and oxygen make water and carbon dioxide. All right? We're maintaining a constant level of carbon dioxide in our bodies, but we make more than our body wants to actually hold on to, so we exhale carbon dioxide. So the loss is basically those things that we lose through the process of excretion. Urine, feces, exhaling, sweating, these are all different processes of excretion. We'll go through each of these steps when we get to those sections. And also those things that we're actually breaking down. Glucose, we're destroying, and we're making something new, but we've destroyed something in the process. All right? Now, homeostasis is not equilibrium. All right? We're trying to maintain a constant environment with homeostasis. Equilibrium means things are the same. Now, remember we talked about the extracellular fluid compartment and the intracellular fluid compartment. All right? Now, if you were to look at these two things, you would say that, oh, they're relatively stable. There's not a lot of movement between these compartments. They have the relative number of solutes. In other words, the number of solutes that are found, and solutes are basically every molecule you can think of in your body, all right, excluding the water. The number of solutes that's found in the extracellular fluid is roughly the same as the number of solutes that are found in the intracellular fluid. The thing is that those solutes are different in each of those two compartments. Osmotically speaking, they are the same. All right, so there's balance in terms of osmolarity, but not in terms of what the actual substances are. And if you look down at this bottom graph, this kind of shows you. We have sodium, potassium, chlorine as the three major ions, and bicarbonate, plus some large anions that we're just kind of saying large anions, which are basically negatively charged proteins. If you look at the extracellular space in the interstitial fluid, there's way more sodium than there is in the cellular compartment. Conversely, potassium in the second group, there's so much more potassium inside cells relative to outside the cells. Chlorine, lots of chlorine outside the cells, very little inside the cells, and you can just do the comparisons. So what we have here is we have an imbalance of the particular type of solutes that are found in each of the compartments. So what we say is that our body lies in a state of chemical disequilibrium, even though we are at a relatively constant or stable osmolarity. Does that make sense so far? All right. Now, the reason we're going over this is because we're going to talk about movement. All right. The other thing is because of this imbalance of where the ions sit, is that we're going to have what is also called electrical disequilibrium. Now, that doesn't mean that you are charged. If you take all the ions in your bodies, take all the negatives and all the positives and put them together, you're going to basically be neutral. All right? You do not carry a charge. I can't walk up to someone and they shock me automatically. They have to rub their feet in socks on shaggy carpet. All right? That's static electricity. But they don't carry a charge. But because of the imbalance, what we have are, in some cases, more positive charges on one side of a cell and more negative charges on the other side of that membrane. And so that's that disequilibrium. Now, this osmotic equilibrium and the chemical and electrical disequilibrium is dynamic. And it's a dynamic steady state. In other words, the disequilibrium is out of whack all the time. And that's okay, because there's going to be constant movement of materials back and forth between these compartments. So dynamic, you're moving stuff all the time, but because everything's moving all the time, there's really no change at all. We say it's a steady state. The way you can think about this is think about the UC Underground and think about females and males moving in and out of the UC Underground. Okay? Now, if females are negative charges and males are positive charges, you have females moving in, females moving out. Males moving in, males moving out. Grand scheme of things, nothing's really changed. Right? And that's what we're kind of looking at. In the big picture, nothing's really changed. But what we're going to do is we're going to start focusing on those individual molecules. And most of you are going to sit here and go, oh, I can't believe we're going to talk about this again. I've seen this at least 3 different times in at least 3 different lectures. But that's what the first 5 weeks of your class is. Everyone on the same page so we can move forward. All right? Now, in order to get these things to move back and forth across these into these different compartments, we have to move back and forth across these membranes using different transport mechanisms. And we have to rely on the permeability of that particular membrane. Now, the first and the easiest one, and we're not really going to even talk about this other than this broad definition until we get to the circulatory system and respiratory system, is something that's called bulk flow. Now, remember back to earth science back in 7th grade. You guys remember that class? It's the one you slept through? It's the one taught by the coach? They told you that air has a certain composition. What is air made of? Nitrogen, oxygen, and a whole bunch of other gases. So predominantly nitrogen, very, very little carbon dioxide, and then a whole bunch of other gases that are even less than the carbon dioxide. All right? Now, which of those gases does your body need in order to do metabolic activity? Oxygen, right. And so when you breathe in, are you selectively taking in oxygen? Oh, there's an oxygen molecule. No. You're sucking in air. You're taking in everything that's in the air into your lungs. Not just those gases, but any other nasty molecule or bacteria or dust particle that happens to be floating around in the environment as well. Moving all of that simultaneously is bulk flow. All right, that's an example of bulk flow. That's an easy one to see. Now, this is also true in the circulatory system. Your blood, which is water plus a whole bunch of solutes, in other words, just molecules, ions to macromolecules, is able to move from a capillary system into the interstitial space through the capillary walls. We'll talk about it in more detail. But basically, it's the movement of all that stuff that can leak through the capillary walls to move that mass of fluid. Bulk flow. Everything at once. So that's the simplest type of transport. Now, in order for this to occur, you need to have a gradient. And you're going to see this word over and over and over again throughout this semester. You'll be tired of gradients by the time you leave this class. When next time you hear gradient, you're just going to go, ah. You'll be driving down a highway in Colorado, 10% gradient. Not again. In order for bulk flow to work, you need a pressure gradient. You need to have a force that forces things from an area of high pressure to an area of low pressure. Now, just going to use this as a time to define some stuff. It's not hard, you guys already know this. I just have to make sure that we all are on the same page. What we're going to be talking about a lot is the permeability of a membrane. A membrane is said to be permeable when it allows the passage of a given substance. A membrane is said to be impermeable when it prevents the passage of a given substance. Now, if you look at a cell membrane, when you look at that membrane, we say that membrane is selectively permeable. It allows certain materials to pass through it, and it disallows other materials to pass through it. All right? What allows our membranes to be semi-permeable is based upon its composition, which we've already talked about. It has the presence of lipids and the presence of proteins. Lipids serve a purpose in terms of its semi-permeableness. We'll look at that in just a moment. And we're going to see how proteins play a role in allowing certain molecules to pass back and forth. In other words, allow for its selective permeability. So what is found in the membrane determines what, and also what's actually not what's found in the membrane, what the membrane is made up of, the lipids and the proteins, is what determines the degree of permeability of that particular membrane, how it is selectively permeable. Now, some general rules. And it's easy to get confused with this stuff, so just pick one side and stick with it. All right? I tend to focus on lipid solubility because most of the work that I did while I was a grad student and as a postdoc dealt with lipid-soluble substances, so I like lipid-soluble. All right? So you look at this stuff and you say, oh, it's lipid-soluble. Fine. We basically have two types of molecules in our world. Lipid-soluble molecules and water-soluble molecules. All right? When a molecule is highly soluble in lipid, in other words, not soluble at all in water, it has a high degree of permeability into a membrane. Why? The membrane's made of lipids. All right? What type of molecules? Uncharged molecules and nonpolar molecules. All right? So, highly soluble if you're uncharged or nonpolar. If you're water soluble, in other words, you're talking about ions which are charged, or polar molecules like glucose, you're going to be disallowed. All right? The lipids will prevent you from actually coming through. Now, just because you're uncharged, does not mean that you automatically get to go through a membrane. You could have the largest molecule in the world that's uncharged, and it will not penetrate the membrane because size matters. Guys? In biology, size matters. All right? The larger the molecule, the greater difficulty it's going to have penetrating through a lipid bilayer. It will either penetrate with great difficulty or not at all. If you're a very small molecule, you can penetrate between the lipid head, move through the hydrophilic or the hydrophobic regions, and pass through just fine. In fact, there's actually an exception that proves the rule in all of this. Water is a polar molecule. You remember learning about that a long time ago? Yeah, there was a whole lecture on that in biology, and then you took chemistry and you had to learn it all over again. Water is polar. Water sneaks through a lipid bilayer because it's a very small molecule. Now, things just don't move across the membrane. Once again, we require a force to drive molecules across the membrane one direction or the other. And these forces are going to fall into one of two categories. You're either going to be passive, in other words, you don't require energy to do it, I mean in the form of ATP, or it's going to be active, where it requires the energy and the force of ATP to be used to direct movement. So when we're looking at these transport mechanisms, kind of keep in mind, am I using ATP here, am I not using ATP? And it's pretty easy because we call it active transport or passive transport. So it's not too difficult. And if I go too fast or you have a question, just feel free to stop. So these are the basic types of membrane transport that we're going to be looking at. We have diffusion, protein membrane transport, which is broken down into three different types of facilitated diffusion, active transport, and secondary active transport. Then we have vesicular transport, and finally osmosis, which everyone likes to cry about. Which really is actually very simple. We just make it a lot harder than it actually is. Now, diffusion is the most simple form of transport. All right? What we're doing is we're moving a molecule from an area of high concentration to an area of low concentration. In other words, what we're doing is we are moving down a concentration gradient. There's that word again. So sorry. Like I said, it's going to keep coming. All right? And again, what we're going to do is we're going to reach a steady state. In other words, in diffusion, you are trying to reach where all the molecules have the same amount of space around each other. All right? So there's an equal distribution of all the molecules within a given space. And you see the pretty little picture that I pulled out of your textbook. Get some Kool-Aid, drop it in a thing, watch it slowly diffuse. Now, some features about diffusion. All right? First, it's passive. Does not require any external energy. Things will just move. In our little picture here, we have two areas, area A and area B. We have lots of molecules in area A. We have very few molecules in area B. Over time, what's going to happen? The molecules in A become uncomfortable because everything's in its space. Got to move away. Don't like other dots touching me. And so molecules from area A are going to slowly diffuse into area B, moving down the concentration gradient. All right. Now, does that mean that molecules in area B don't move at all? They just happily accept area A molecules to show up? No. They're happily moving over into area A where it's very, very crowded. Those are your extrovert dots. Actually, what's going on is molecules are just moving randomly. Molecules in area A are moving around in area A, but a majority of them are moving towards area B. A few molecules in area B are moving into area A, and so what we see is we take the movement of molecules in A to B and look at the molecules moving from B to A, add them up, and what we're going to see is that we have diffusion that is net diffusion, in other words, the sum moving down the concentration gradient. All right? Now, if you take all these molecules and divide them up so that they're equally spread out in both of these areas, movement doesn't stop. We still have molecules moving back and forth, but we don't see any discernible movement because there's equilibrium. 10 molecules that move from B to A is going to be matched by 10 molecules moving from A to B. That's the equilibrium portion. Now, there's some rules about diffusion. We're going to look at Fick's law in just a second, but these are some general rules. The steeper the concentration gradient, the faster the movement. Now, this is easy to visualize. If you get on a skateboard in Houston on the sidewalk, is there movement? No. Why? It's flat. There's no gradient. If you get on a skateboard on a half pipe, for those of you who don't know what a half pipe is, it's that thing that looks like a half of a pipe. See, it's real clever, very clever. And at the top, it's basically 90-degree angle, which slowly will change, right? Will you move fast at the top of the half pipe? Yes. Why? Steep gradients. Right. All right. Same rules applies for a gradient. If you had 1,000,000 molecules over in A and 1 molecule in B, are those molecules in A going to move very quick? Yeah. There's a lot more space over in B. Let's rush over there. So higher concentration gradients, steep concentration gradients are going to increase the rate of diffusion. The shorter the distance that a molecule has to travel, the faster the rate of diffusion. If you have two areas that are side by side like this, molecules can move pretty quickly. If the two areas are spread far apart, then you have to move a further distance, so the rate of diffusion slows down. Temperature, you can equate that to energy. If you raise temperature, the molecules have more energy. They're absorbing energy in the form of heat. They tend to move more, so they're going to move faster. Lastly, small molecules have a tendency to move a lot easier than large molecules. They don't bump into each other much. You can think of this as 3-year-olds in a crowd. Oh yeah, I forgot. No, I'm the only one here that probably has 3-year-olds. You get 3-year-olds and you put them in a room of adults. They're zipping between all the big adults. Big adults have to bump into each other and say, "Pardon me," every couple seconds. All right. Smaller the molecule moves, quicker the rate of diffusion. Now, diffusion can happen in an open space, much like the picture that we've shown here, or it can occur where you have something. Oops, I always forget to do this. Something that divides the two spaces. In other words, if you have a membrane that is permeable to the substance that is diffusing. All right? In other words, where there's a partition. So, there is a law regarding diffusion. It's called Fick's law. And you can just summarize it in we've already looked at some of these. Just summarize it in this way. Certain properties regarding a membrane are going to affect the rate of diffusion. First is the magnitude of the concentration gradient. We already mentioned that. The degree of permeability. Now, the degree of permeability is, like I said earlier, about 2 slides ago, is dependent upon what the membrane is made up of. Lipids and proteins. All right? If there are a lot of cholesterol molecules, or if the lipids are made up of primarily trans molecules as opposed to cis molecules, the lipids are going to be a lot closer together, right? And so it's going to be harder to sneak in between. But if you have a whole bunch of cis molecules that have that thing that sticks out so the molecules can't come close together, it'll be easier to move through them. I'm sorry, I always talk that way. All right? So, depending upon what the membrane is made up in terms of the lipids, but it's also the proteins. Because many proteins are transport molecules, carrier molecules. And so the more carrier molecules and channel molecules you have, quicker the rate of diffusion across that membrane. The fewer you have, the less diffusion. Surface area. The more surface area you have, the greater the rate of diffusion, and this should make sense. If we yelled fire, which we're not going to do, and we all had to go out just this one door, could we all get out fast enough? No, but we have multiple doors. I'm going to play airline stewardess here. Multiple doors, and so that increases the door surface area of this room. Could we all get out fast enough? In theory. Right? So, more surface area, the better. Last is the thickness of the membrane. All right? Now, as far as a cellular membrane is concerned, they're more or less the same thickness. But we're going to look at the lungs, for example, and we're going to see cells that are very, very thin. And then underlying those very, very thin cells is a very, very thin basement membrane. And underlying that basement membrane is a very, very thin capillary. And an oxygen molecule has to cross between the cell, the basement membrane, and in through the capillary epithelium in order to get into the bloodstream. Now, if we make that all very, very thick, for that oxygen molecule to get through, we want it very, very thin, so it can diffuse very, very quickly. So the thickness of the membrane should have to travel plays an important role. So these are the things that affect the rate of diffusion, that are properties of a membrane. And there's a nice little list right there. Now, diffusion is the simplest form of membrane transport, and it's really not even transport, it's just movement across the membrane. Most of the molecules in your body fall under the category of lipophobic. The other term for it would be hydrophilic. It likes the water. Or you could say that they're electrically charged. They're one of these two categories, hydrophobic or electrically charged. And so by that very definition, they cannot penetrate the lipid bilayer on its own. It requires help in the form of a protein. These are going to be membrane proteins. And what results from this is protein-mediated transport. Two different types. We have facilitated transport, by definition is passive. When you reach equilibrium on both sides of the membrane, that facilitated transport stops. There's no more concentration gradient driving the transport. So if you have high concentration of hydrophilic protein over here and you want low over here, and you have a molecule that's capable of transporting it, you'll keep moving those molecules until there's equilibrium on both sides of the membrane. Then we have active transport. An active transport actually requires energy from ATP, and what we're going to be doing is we're moving substances against the concentration gradient. In other words, this is akin to trying to lift something from the floor and putting it on top of a shelf. It doesn't want to go up to the shelf. The shelf is high. It's going to require energy to move things up. Using those molecules, you have high lipophobic molecules out here, low lipophobic molecules in here. You're trying to move these molecules across the membrane to some place where it does not want to go. That's why it requires energy to do so. Now, before we go and look at the specific type of proteins, I want to point out there are different types of membrane proteins. We're going to be spending some time on a lot of these a little bit later, but just to introduce us to them, we first have structural proteins. We have enzymes that can be found located at the membrane. We have receptors, which we're going to spend a lot of time talking about over time. And we have our transporters, which we're going to focus on today. The structural proteins, simply put, are those molecules that make up the cytoskeleton. In other words, they establish the shape of the cell. They help create the cell junctions between cells. They stabilize your tissues. Anyone ever get an Indian burn? You know what an Indian burn is? Yeah? Indian burn. That's when your big brother holds you down on the ground, grabs your arm, and twists in opposite directions. Yeah, see, people are going, yeah, I remember that. Yeah, it is good stuff. Do you know why your skin doesn't come ripping off? Because of the cell junctions created by the cytoskeletal network. All right. This helps to establish or attach cells also to the extracellular matrix. In other words, allows the tissue to lie and hold in place. Other type of proteins that can be found are enzymes. The purpose of these are to catalyze chemical reactions at the cell membrane. This can occur, basically it's usually occurring on the inside portion of the cell membrane. All right. Usually in response to a chemical signal from the outside, from the external environment. And so this is one way that we can actually have cells communicate with one another. You cell, I want you to do this. Yes, sir, and it starts doing it. That's what the enzyme is. It's the doing part. The receptor, which I have just a really crude example up here, is the thing that receives and responds to a chemical message. Now, I told you guys on Tuesday that I was a reproductive biologist, and so I use a lot of my examples here. One of these molecules that we can think of a hormone would be follicle-stimulating hormone. Now, follicle-stimulating hormone is found in males and in females, follicle-stimulating hormone promoting the folliculogenesis of the ovum in the female. And in males, it promotes spermatogenesis. All right? It's a molecule that's made in the brain. All right? Hypothalamus. Oh, no, you're right. Anterior pituitary. Excuse me. I was getting ahead of myself. Thank you. Anterior pituitary. But its action is in the gonad. Okay? It goes into the bloodstream, travels very, very far away, to your gonad and says, hey, cells, this is what you need to do. That's what the receptor is responsible for. There is a follicle-stimulating hormone receptor that receives that chemical message from the brain and then tells that cell what to do. Now, these receptors aren't just playing a role in that. It also plays a major role in vesicular transport, which is what we're going to look at today. Lastly are the transporters. And this is what is responsible for actually moving molecules from one side of the membrane to the other side. basically fall into one of two categories: a channel protein or a carrier protein. Now here's the beautiful thing about biology: we name things for what they do or for what they look like. A channel protein acts like a channel. Yeah, see, very, very simple. And a carrier protein carries, takes it from here, moves it over there. All right. So with a channel, we're actually literally creating an opening between the extracellular fluid and the intracellular fluid. It's a water-filled passageway that allows the movement of molecules from one side to the other. Very, very rapid movement. And what type of movement are we seeing? Diffusion, down a concentration gradient. All right. We basically put a big gaping hole. It's not really big and it's not really gaping, but you can get the visual image. It's a hole that allows diffusion to take place. With the carrier molecule, we're binding something very specific. You're supposed to be over here. You can bind to me, and I will carry you over here once I'm bound. And once you're unbound, then I'll go back over here and look for the next one. Literally carrying it across. When this happens, and you can see in this little image, I know it's a cartoon, but this is literally what they kind of look like. There is no direct connection. Here in the channel, we can see there's an opening on either side, so there's a direct connection between the extracellular fluid and the intracellular fluid. Here, you're either open to either the intracellular space or the extracellular space. You're never creating a channel. So you're always rate limiting. You have to bind something, turn the other way, then let it go. The difference is that channel proteins generally work on very, very small ions, whereas carrier proteins work on larger molecules. I throw this up here not for you to memorize. It's just a nice way to actually see how everything is kind of organized. And we're going to be seeing how we have different types of channels, both open channels and gated channels, and different types of gated channels. But you can see, here's your membrane transporters, structural proteins, membrane enzymes, receptors, and see how they kind of just break down, and then it's all this stuff right here are your transporters. It's just different families and just breaking it down. So we're going to start with the channel protein. All right. Now, as I said, this is something that creates a passageway between the intracellular fluid and the extracellular fluid, and really what we have is basically a molecule that passes back and forth several times through the plasma membrane. In other words, it has a hydrophobic center, and it's one of those integral proteins that we talked about. The difference is that the way that this thing is bent and twisted is that it actually creates a pore through the center of the molecule. In our little cartoon here, it's basically showing you a series of rods. But you can imagine that each of these rods are connected like so, and that would be your molecule, like that. And what you have is a channel or a pore that goes right through. And all the amino acids that make up this rod have particular charges that allow or disallow a particular ion to actually pass through it. So this channel is actually pretty small. And we're going to be talking about, very specifically, we're going to be talking about sodium channels and calcium channels and potassium channels. And we're going to use some very specific terminology in those sense. This is a sodium channel. But I just want to let you know, for those of you who are interested, that there's no such thing as a single sodium channel. There's like 240 different sodium channels in the body. And they're different depending upon where they're found, and they have different properties. But they all just allow sodium to pass through them. And there's many different potassium channels. All right. So when I say sodium channel, I'm just kind of using, like, this is the general term, sodium channel. All right. So what do these channels do? We allow the diffusion of ions, and I have over here in parentheses, and water, because there are specific types of channels that allow for the passage of water through them. They're called aquaporins. All right. So they allow the movement, the diffusion of ions down their concentration gradients. Now, they're very selective. It's determined by not only the diameter of the center of that pore, but it's also determined by those amino acids that I was talking about that have those electrical charges. All right, think about your periodic table. Sodium is a smaller molecule than potassium, right? They both have the same valence, +1, right? So if you had a potassium channel, you might think, oh, well, sodium is smaller than potassium, it should be able to zip right through that channel. And that's not the case. Even though we draw this nice, pretty little picture of rods with a kind of a center pore, it doesn't look like that. There's all these charges in there that prevent the movement of ion, even though it might have the same valence and it might be small. Potassium channels are specific to potassium. Sodium channels are to sodium. You can have a cation channel that is non-specific except for cations. You can have an anionic channel which is specific to anions. You have a chlorine channel specific to chlorine. So there's a high degree of specificity to these things. Now, all channels have a particular region within that rod structure that I talked about that acts as a gate. All right? And we're using the term gate just like you would think of there's a gate in front of my house that keeps the goat in my yard. No one has a goat in their yard? Actually, I had a friend who had a goat too. It was very mean. He'd go up and it'd butt you. I don't know why. Anyway, it's really literally a gate, something that can swing open and close. But we classify channels in one of two types. They're either considered to be open or closed. An open channel spends most of their time in the open state. In other words, their gate never really closes. There's no natural condition in which that gate actually closes. Another term for this open gated channel is called a leak channel. If we're talking about a water channel, then we'd refer to this as a water pore. In other words, you can just think of it as a big giant gaping hole surrounded by a protein that allows the passage of that particular ion through it all the time because that gate never closes because the goats are going to leave. The closed channel is where you have a gated channel, and we actually call these gated channels because the gate actually moves. All right? It spends its time mostly in the closed state until it's stimulated to open. All right? And so it literally regulates the movement or the passage of those ions through that gate. Now, there's many different types of gated channels, and I've thrown up 3 here, but there's actually more than this. We have chemically gated channels, where you need to have a molecule of some sort come and bind to the channel, which serves as a key to open the gate. Voltage gated channel is where you have a change in membrane potential, which we'll talk about in the next lecture, where it causes a change in the shape of the molecule, which opens the gate. We have mechanically gated channel where we actually twist the cell membrane, which causes a change in the shape of the molecule, which opens the gate. This is how touch receptors work. All right? So we have different ways. There's also another one. Can anyone think of one off the top of their head that I didn't listen? That's like that. Yeah, that'd be chemical. What's another one that you might think of? Thermal. Well, baro would be good too. A baroreceptor deals with pressure, although that falls in the category of mechanically. Thermal channels would be another one, where changes in temperature cause a gate to open. Just another one, but I mean, you kind of get the idea. So those are the different types of channels. Now you're probably again sitting here thinking, okay, he's going through this stuff, why? I'm trying to set up what we're going to be looking at over the next couple days, which is going to be the movement of these ions back and forth. All right. The second type, and again, stop me if you ever have a question. All right. If you feel like you're really falling asleep and you're desperate to stay awake, you can ask me a question. If you want to sleep, that's fine too. Like I said, I was the guy that sat in the back row and slept. The difference was my professor talked like this, usually with a German accent. Well, I have one specific example of that. All right, I'm going to give you my worst story ever. I've got 30 seconds I can do this. I took a calculus, no, it was a chemistry class, I think. I can't remember at this point. Anyway, the professor was a German professor. In other words, he came from Germany. Very, very thick accent, introverted, ambidextrous. And what he would do is he would talk to, and this was an auditorium class, so just like going to SEC 100. And he, instead of facing the class and doing whatever work that he was doing, he faced the board. He would write with this hand, talk to the board in this heavy German accent, and erase with this hand. By the second or third class, everyone was sitting away on the edges, praying they could see what he was actually doing up there. I think he was drawing cartoons, to be real frank. I don't know. Carrier molecules, on the other hand, are different than the channels. Remember what I said, they bind very specific substances. And what that substance, it binds, when it binds to it, it causes a change in the shape of the molecule so that the molecule changes to the other side of the membrane, and at which point that binding site where that molecule bound releases it, and the molecule can now be set free and move. A lot of different molecules move this way, both small organic molecules as well as ions. All right. Obviously, when you have a mechanism where you have to go through several conformational changes to get to open from one side to the next, it's going to be slower than a channel. All right. It's like going through a door. You have to go to the door, turn the door, open it, walk through, close the door behind you. That's, in essence, that's a lot slower than just walking through a doorway. All right. So we never have a continuous passage. And so what we're doing here is we're actually regulating movement. Now there's different types of classifications of carrier proteins. We have uniport carriers, which means we're carrying one kind of molecule. In the example here, this right here, glucose, this is a glucose uniport. Most of our ones that we're going to be looking at are going to be co-transporters, and what we're dealing with is we're carrying two molecules. We can carry two molecules in the same direction, which we refer to as symport, or we can carry one molecule in one direction and another molecule in the other direction, which is considered antiport. Now, when you use a carrier to transfer a molecule across a membrane, we refer to this as facilitated diffusion. Why is it facilitated diffusion? Because we have a carrier molecule and we're moving down our concentration gradient. So it's a passive process. It doesn't require energy. Now, the binding site for this particular molecule has the same degree of affinity on either side of the membrane. But because we have a concentration gradient, we're going to see molecules moving in the direction of the concentration gradient, down the concentration gradient. Now, obviously, if you had a lot of molecules over here and very few over here, and you have the carrier here, molecules are going to be moving down the concentration gradient until we reach equilibrium, at which point diffusion would stop, right? But very often, the molecule you're trying to moving is something that you want to get a hold of desperately. An example would be glucose. Do you want glucose in your bloodstream, or do you want glucose in your cells? In the cells. That's right. Glucose is valuable. We spent a lot of work standing in that line at Taco Bell to get that glucose in our bodies. At least I did this morning. All right? So we don't want that glucose not to be doing anything. We want to get inside the cell. But because of that problem, it's a basic chemical property, when it gets at equilibrium, that's a bad thing. So what we're going to do is we're often going to use mechanisms to turn the molecule on the downstream side into something else so that we can continue that concentration gradient. And that's what we see in this little example here. So, lots of glucose on the outside, so see, high glucose out here, low glucose in here. We're going to move until we get equilibrium. But because we don't want equilibrium, let's take our glucose, let's phosphorylate it, and we get a whole new molecule. This is that law of mass action I'm talking about. All right, what we've done, instead of allowing there to be balance, we've changed something so that we keep it in imbalance. All right? Yes?
Is that because they move independent of each other's gradient?
That's right. Well, because really what you're doing is you're monitoring, or, well, okay, you're asking me a chemistry question, which I really don't have an absolute answer for. All right? But in essence, what you're doing is because whenever you change a molecule from, just even a simple phosphorylation, a simple loss of an electron or something like that, what you've done is you've changed its very nature. It's no longer in balance with, it's not an isotope, but basically it's no longer the same thing, right? And so if you no longer have that same thing there, you basically have created, an imbalance. Exactly. So if you go back to that law of mass balance thing, what we've done is we've had a chemical reaction where we've catabolized this, or actually in this case we've anabolized this molecule into something entirely new. So we've lost the glucose and we've created glucose 6-phosphate, which is a completely different chemical.
You anabolize and you catabolize.
And then when you want the glucose, then you catabolize it. Well, does that make sense though? All right. So it's taking the cookies off the plate, right?
Put it in your pocket, or you can
That's right. Doesn't matter what you do with the cookie. You don't have to shove it in your mouth. You just put it in your pocket. Give it to your friends. Have a party. Just keep 4 cookies on the plate. Does a facilitated diffusion make sense? Okay. Active transport, on the other hand, is going to require energy because we're moving molecules with a carrier against the concentration gradient. In this case, the binding site in that carrier molecule has greater affinity on the downstream side. In other words, here's your concentration gradient. You're going to be moving things this way. The affinity for the molecule is greater when the carrier is facing this direction. All right? When it's facing this direction, less affinity, so it's going to force that molecule to pop out against its will. Now, there are 2 types of active transport. Primary active transport, this is where we're going to use ATP directly. In other words, we're going to utilize ATP, take that energy to change the shape of the molecule. All right? Most of these transporters themselves are ATPases. They do it directly. And we usually refer to these transporters as pumps. And we're going to see the example, the classic example, that we see in every biology class, the sodium ATPase pump. But there are many different pumps. The calcium ATPase pump. There's a proton punch. You've heard that one too. All of these are basically ATPases, and we're moving things against their gradient. The other type of active transport is secondary active transport, and this is the one that actually confuses people because it requires you to remember some of that physics that you hope that you didn't have to know outside of the MCAT. Remember, how many types of energy are there? Basic, remember we're talking physics for kindergartners here. Thank you, kinetic and potential. Kinetic is the energy of motion, and potential is stored energy. Every time we move a molecule against its gradient and stack it over here with other molecules, we are creating a steeper and steeper and steeper concentration gradient, right? When we have a steep concentration gradient, what do we have over here? Potential energy. And what we're going to use is the potential energy we have stored in this process to drive diffusion against the gradient. You're going, huh. Well, we'll show you an example of that too. We'll see. But mitochondria is a very good example of this. The binding site affinity? Simply put, binding site affinity is where a binding site is where a molecule is going to actually bind to the carrier, right? The affinity is how strongly it binds to. All right? So if you have a molecule that has a strong affinity, it will bind to that binding site and it won't let go. All right? If it has weak affinity, it'll fall on and fall off, fall on and fall off, right? And what you want to hope is that at one point when it's bound to, that it'll flip over. All right? So when you have high affinity, there's a high chance that the molecule that you want to bind to it is going to bind and stay attached. I'll show you an example on the next slide. Okay? Because the next example is the sodium potassium ATPase pump. You can all groan now. Go ahead. Oh, I've seen this 1,000 times. Why are you showing it again? Well, because you got to see this every time we talk about something, this guy's going to come up. All right. So here we have the sodium ATPase pump, and I know we haven't talked about the concentrations of sodium and potassium all that much, other than the little picture that I showed you at the very beginning of class. But you have to imagine, inside the body, we have very, very low levels of sodium inside cells, very, very high levels of sodium outside the cell. So we have a concentration gradient favoring the movement of sodium into the cell. Conversely, we have very, very high potassium levels inside the cell and very, very low potassium levels outside the cell. So we have a concentration gradient going the other direction, favoring the movement of potassium, moving the potassium inside the cell. Did I get that? Excuse me, outside the cell. Did I got them backwards? See, I told you I can make mistakes. I'll be the first one to admit it. All right. Now, how do we get into this case? Now, remember, in the case, if all we have is diffusion in our lives, all right, then eventually we're going to see equilibrium where we'll have the same amount of sodium on both sides, same amount of potassium on both sides. And it's the sodium-potassium ATPase that allows us to move these molecules against the direction that they want to go. So, what we have is something pretty simple. We have a molecule that can either bind 3 sodium at a time or 2 potassium at a time. In fact, the binding sites for sodium and potassium overlap each other. So if you bind the 3 sodiums, there's no chance you're ever going to bind potassium. Now, remember what I said about conformational changes, right? These molecules are changing shapes. Even though we draw little pretty cartoons that look like this, all right, that's not just, they're just not rocking. They actually change the shape. And the binding sites are dependent upon which shape they're in. When we're open to the inside, the binding sites have a greater affinity for sodium. And so with the low levels of sodium, they're just going to wander around, and every now and then one of those sodiums is going to find that binding site, sit there and go, aha, I found home. All right? It's like finding a papasan chair. You guys know what papasan chairs are, right? Okay, they were big in the 70s, the 80s, and the 90s in frat houses and other houses. Basically, they're those wicker chairs that you can... Oh, never mind. They're very comfortable. The bowl things, right? They look like walks, except you can move them any way you want to. Don't look at me like I'm that weird. Go ahead, Google it while I'm talking. It's fine. All right. Anyway, so when you're open, sodium is going to move its way in, and once those 3 sodiums bind, that binding is going to cause a change so that we can actually hydrolyze ATP. When we hydrolyze ATP, that's going to cause the change in the shape so that it opens up to the outside. When it opens up to the outside, that binding site where sodium was has changed shape. So it's a lot like those binding sites basically kick out the sodium. Say, you don't want to be here anymore. I no longer am attracted to you. And so the sodium pops out. But in the same time, what's happened is that the potassium sites have come about. You now have a greater affinity for potassium. And so potassium, which is really in low concentrations on the outside, basically says, oh, all right, well, I can wander in here, and boom, I found a site. And much like the sodium, when it found its comfort when it was open the other direction, potassium's like, ah, I'm here. When you get those 2 potassiums bound, that's going to cause a change in the shape again, and it pops the other direction, causing a change in the shape of the binding site, which pops the potassium out to the inside of the cell. Now, we had a lot of potassium in here. But really, potassium has no place to go but in this direction when that thing opens up. Sodium wants to stay inside the cell. But because it's so attracted to the inside of the carrier, when it binds to it, it's going to be happy. And so when it opens up the other direction and gets popped out, it has no place to go but in where that high concentration is. And so what we've done is we've used energy in the form of ATP to make that change so that we can move molecules into a place where it doesn't want to go naturally. All right? And what we've done, in essence, is we've actually established the gradient that we're going to be working with for a majority of the class time. All right? We've actually created the gradient where we have high sodium on the outside and low potassium on the inside. And we created this gradient because of the way that this thing works. And by moving these molecules in different directions, what we've also done is we actually are regulating the cell volume. We've decided what the solute concentration is going to be inside the cell, so we're actually deciding what the water concentration is. And also, because we've moved things in the direction that they don't want to go, remember we created those gradients. We now have a very steep gradient where sodium wants to come inside the cell. We have a steep gradient where sodium wants to go, or potassium wants to go outside the cell. So we have a lot of potential energy that we can now exploit to move other things. And that's where secondary active transport takes advantage of, is this potential energy that we've created. And this is a classic example. This isn't the only example, this is the classic one. The sodium glucose co-transporter. How many of you have ever been to a club that has ladies' nights? Who's going to admit it? All right. Now, like I said, I went to school in New Orleans. Most of the places that had ladies' nights had cover for the guys who wanted to go on ladies' night. Right? What a great, ingenious plan if I'm an owner of a bar. Right? I will charge guys admission, let the girls come in. I'll get 1 million women in here. Guys are going to be clamoring to get inside, and I get to charge them money just to show up. Now, every now and then, you know, and it would limit the number of guys that come in. The only way that you could get a guy to come in with, you know, if there was already the show that they wanted it to do, is if you had some girl tell the bouncer, oh, he is with me. No, this guy's with me. Drag him in. Now, what we have here in our little example of sodium glucose transport is very similar to that situation I described. Sodium is allowed to come into the cell. Why? Concentration gradient. Sodium wants to get in. It has no problem getting in. Oh, yeah, I can go in. All right? The bouncer is our carrier molecule. It's happy to let sodium in. But, you know who really wants to get in? Glucose. But the ratio of glucose, well, lots of glucose inside the cell. More glucose than the cell really needs. It's basically converting it and storing it away. So the concentration of glucose on the inside of the cell is relatively high to what's on the outside. Relatively low. But we don't like the glucose out here, right? Because we spent a lot of time at Taco Bell. Worked very hard for my 89-cent taco. All right? But the glucose doesn't do us any good out here. So, glucose goes up to sodium. Psst, can you get me in? Sodium says, sure, I know a way. Come with me. They go to the bouncer. Sodium pops in and says, hey, I'm ready to go inside. And in doing so, what it's done is it's made a change in the shape of the molecule. That change in the shape of the molecule now has high affinity for the glucose. And so when glucose binds, that is what's causing the change. Both sodium and glucose binding at the same time causes the change in the shape. Now, when that change in the shape occurs, that's going to cause a change in the shape of the molecule to pop out the sodium. When sodium leaves, well, that's the shape of the molecule, so glucose is forced to leave. So what we've done here is we've moved something against its concentration gradient, glucose, by using something that wanted to move down its concentration gradient, the potential energy, sodium. All right? Now, why is this advantageous? Why don't we just use ATP? How much ATP do you get from a single molecule of glucose? 36 to 38. That's mathematically what we get. In the real world, it's probably a lot less. Now let's imagine you had to use an ATP for every single solitary glucose. Is that energy efficient? Would that meet the green standards? No. No, remember, we want to conserve our energy for more important things. All right? We don't want to spend energy moving things that give us energy. So by using the potential energy of moving 3 molecules and 2 molecules at the same time, we are now able to move multiple glucoses for a far less cost. All right? Does this system make sense to you? All right. So usually on these tests, what I'll do is I'll ask which of the following is an example of secondary active transport, and it's usually going to be like this. Or I'll say, you know, here is like the definition of secondary active transport. All right. Now, secondary active transport, movement of amino acids, any sugars, movement of a whole bunch of different things can be done in this way. All you're doing is taking advantage of the concentration gradients that you have established using the sodium ATPase pump. Now, there are a couple of other things about carrier-mediated transport. There is a certain degree of specificity for the molecules. In other words, they are specific to either one molecule or a very, very select few number of molecules. In other words, those molecules are very, very similar to one another. All right? And this isn't even always the case. So in our example, we have glucose being able to bind to, or a receptor being able to bind to glucose as well as galactose. But that's not always going to be the case. All right? They may be able to bind the same thing. So there's a high degree of specificity of carrier-mediated transport. Also, when you can bind to more than one substance, you are going to be subject to competition. In other words, if you're trying to get glucose across the membrane because that's what you want, but you have high levels of galactose, the rate at which you're going to transport glucose is dependent upon the number of glucose plus the number of galactose molecules and the ratio therein. All right. Last thing is saturation, and this deals with the actual numbers of carriers, number of binding sites. All right. You can increase the rate of transport and saturating the number of receptors you have. Once you've done that, you've reached a threshold, and the only way you're going to be able to move things faster is if you have more receptors. So if you want to move 1 million glucose molecules in under a couple seconds, you're going to have 1 million receptors for it. If you only have 5 and you can only move a couple of glucose molecules every couple seconds, you're going to be moving glucose for a very long time. You've reached that threshold. Vesicular transport, and I'm probably going to end on vesicular transport, depends on how fast I get through it, and usually I don't get through it, so we'll probably stop before we get to osmosis, is the mechanism to move very large molecules, macromolecules, particles, bacteria, across a cell wall, all right, because it's far too big for either a carrier or a channel, all right. And what we're going to be doing is we're going to create membrane-bound compartments. In other words, a lipid bilayer that makes up the compartment itself, and it comes from the cell membrane. Now, there are 2 processes that are responsible for intaking materials into the cell, and 1 process that outputs material. In other words, we have specialized names for these different processes. We have phagocytosis, endocytosis, and exocytosis. Now, technically, I guess you could say phagocytosis is the same thing as endocytosis, except we've actually refined the definition to distinguish between the 2. Because phagocytosis is cell eating. All right? This is a process that's mediated by actin of the cytoskeleton. What that means is that it requires ATP. In our little example here, we have a macrophage that is about to devour a bacterium. And so what we're going to do is basically, when the bacterium comes in contact with the macrophage, it's going to actually cause the actin to change shape. In other words, cytoskeleton changes shape. And what you see is the shape of the cell work its way around to engulf the bacterium. And then what you've done is you now create a compartment that is a portion of the cell wall. All right. Now, once this compartment is created and it pinches off and creates this little phagosome, that phagosome is going to come into contact with another cellular compartment called the lysosome. And the lysosome contains a whole bunch of enzymes that are responsible for digesting whatever is in the phagosome. Now, in order for this to work, you're going to need, but the big benefit is that you get a whole bunch of stuff out of the destruction of whatever's inside that phagosome. And again, the thing that triggers the whole reaction is the bacterium itself. It serves as the signal. It's recognized, and that's what's going to cause the activity. Now, it doesn't necessarily have to be a bacterium. It could be cellular debris. For example, like when you get a cut or a wound, there's cellular debris, and so phagocytosis occurs by taking up those dead cells. That's phagocytosis. Endocytosis, there are 3 different types. Pinocytosis is basically a non-selective uptake of the extracellular fluid. In other words, what you're doing is you're sending out a little pseudopodia and going like this and making a little tiny vesicle that is intaking whatever's there. Pinocytosis means cell drinking. So back in the day it was phagocytosis and pinocytosis, and they fell under the family of endocytosis, but they've actually defined it a little bit more. So pinocytosis is a non-selective uptake of the extracellular fluid. You're not actually looking for something specific. It's just whatever is there, I'm going to take it in, and whatever I can find useful, I'll use. Then we have receptor-mediated endocytosis, and this is where you're going to selectively uptake large molecules. What we have are regions on the cell membrane that have high concentration of these proteins that are called clathrons. All right? And what happens is that you have receptors that are out there looking for a specific cellular message. When the receptor gets bound by the ligand, the cellular message, it migrates to and binds with the clathrin. which will then cause the invagination of that region and create that vesicle. What we're doing is we're transporting a whole bunch of substances inside the cell simultaneously. So we're talking about hormones, growth factors, other bindings, other proteins as well. I'll show you a picture of this on the next slide. The last one is podocytosis, which is kind of like receptor-mediated cytosis, but there's a slight difference. Don't have clathrin-coated pits. You have something that are called calveoli. And what you have in these calveoli are lipid rafts and these lipid-anchored proteins. So it's not clathrin that's actually bound within the membrane. And what we're trying to do is we're concentrating molecules and internalizing them. And very often you'll see podocytosis used in some very specific systems, and one of them is when we're talking about transepithelial transport in the capillary system. In other words, moving things from one side of the capillary to the other. And I'll show an example of this in a moment as well. So this kind of shows two steps, because it's also going to deal with endocytosis. Receptors on the cell surface, come along, it's the receptor, which causes the receptor to move to the clathrin region. When you get enough of these things bound up, that's going to be a signal to cause the endocytotic process, where you can see the invagination and the closing of the vesicle. The clathrin actually gets recycled. It gets sent right back to the plasma membrane. You're going to see fusion, and/or you're going to see the removal of, say, the receptors so that they can be recycled. And then lastly, you have the materials that you brought in, which can actually be processed. So this is the process of basically getting this into the cell for processing. That would be an example of receptor-mediated endocytosis. All this stuff right here is just an example of exocytosis, which I'm throwing over on a different slide. All right. Here, you're trying to take something that the cell has inside it and trying to put it on the surface or outside of the cell. And in this case, what we're talking about is the receptor. We don't want the receptor inside a vesicle. We want it on the surface of the cell so it can find that ligand. And so the vesicle, which is how we're going to, which contains the receptor, are moved to the cell surface. They fuse with the cell membrane, and then that vesicle opens up, and the receptor is faced in the right direction. All right. Now, you could also have this vesicle full of all sorts of molecules, and when it opens up, where would the molecules go? Out into the space. Pretty simple. So we can do two things. We can either excrete very large molecules, or we can add specific components to this plasma membrane. So epithelial transport, we actually have two different types, or based on their names. Whenever we move any substance through a cell, we have to remember what we're doing. If you're moving things from the lumen of an organism, or excuse me, an organ, all right, I want you to think of the digestive tract for a moment. It's a tube, right? It starts here, goes all the way through, comes out back here. One big giant tube. You are donuts. You will hear me give you this lecture in a little while. Donuts. You are what you eat. All right, but you're a tube. Digestive tract is a tube. That inner portion of the tube is the lumen of the organ. When we're taking things and pushing it into the lumen, that is the process of secretion. When we're taking things and pulling things from the lumen, that's the process of absorption. Okay? Sure, it's up there too. No, it's okay. So here's our tube. When we're putting things into the tube, secretion. When we're pulling things out of the tube, absorption. Is that good? Okay. All right. Now, here we have an example of the digestive tract. Oh, actually, this is the kidney. Oh, no, I guess it is a digestive tract. So lumen of the kidney or so. So what we're doing is we take this molecule and move it that direction. That is the process of absorption. If we're taking this molecule and moving it that way, that's the process of secretion. All right? The whole process of moving things from one side of the cell to the other side of the cell is transepithelial transport. If we're moving through the cell, that is called transcellular transport. If we're moving things between two cells, like that, that would be paracellular transport. Now, this process usually will require something moving against its concentration gradient and then down its concentration gradient. Now, which comes first is dependent upon the substance. If it were glucose, if we have glucose here, glucose would have to move up its concentration gradient inside the cell and then move down its concentration gradient. If it were sodium, it would move down its concentration gradient and then it would move up its concentration gradient. You'll figure this stuff out when you look at this for a little bit longer than 3 minutes. All right? And we'll be going over this over and over again. So this is an example of what I just showed you. Glucose and sodium, where does sodium want to go? It wants to go down its concentration gradient. It's not going to go anywhere without its girlfriend glucose. It's the boyfriend glucose. Glucose has to come in. It's moving up its concentration gradient. So what we're doing is we're moving up, we're moving down, and then glucose can then move down its concentration gradient through a simple carrier-mediated system, and then what we have to use here is active transport to pump sodium back out against its gradient. So we've gone from high to low to high in this example, and here we've gone from low to high to low. Up and down, depending on which way you're looking at it. I think transcytosis is the last slide I'm showing you. Don't quote me. If the next slide says osmosis, then we're on the last slide. So transcytosis is literally moving using endocytosis and exocytosis simultaneously. And this would be the example of podocytosis. See our little caveoli? Taking in some materials. We want to move them from within or across the capillary system. We've gone through the process of endocytosis. We take that vesicle, instead of processing it, we just let that vesicle fuse on the other side through the process of exocytosis. In essence, we've moved these molecules from one side of the cell to the other side of the cell. All right? Transcytosis. When we return on Tuesday, we will finish with osmosis, and then we'll start dealing with creating plasma or protein. We'll deal with potential energies or something like that. I can't remember. Yes, ma'am.